Our next lesson is Balancing Equations 3. And in this lesson, we're going to look at three things. We're going to look at the different types of chemical reactions. We're going to look at how to figure out how to predict reaction products. And we're going to look at how to balance those resulting equations. To go through this lesson, what you're going to want to make sure you have is you want to make sure you have your colored sheet that's titled Predicting Reaction Products. You'll probably also want to make sure that you have your periodic table and your polyatomic ion colored sheet. So, continuing here. There are five major types of chemical reactions that we are going to talk about in this unit. They are synthesis, decomposition, single displacement, double displacement, and oxidation or combustion. And the last one, oxidation or combustion, are simply two different names for the same type of reaction. I will accept either one. If you see this type of reaction, there's no real prevalence for one versus the other. Technically, oxidation covers all types of reactions like this, and combustion covers fast reactions like this. But I will accept either name for that type of reaction. So let's take a look at our first one. First reaction is synthesis. Synthesis, the root here is the word synthesize, that is to create. And so in all cases in a synthesis reaction is we are creating one new substance. And so we talked about before the reactants. The reactants, when we write our chemical equations, are the ones that are reset on the left side. The reactants are generally both elements. So usually it's element plus element. In fact, if you ever see an element plus element on your reactant side, that tells you this is automatically going to be a synthesis reaction. Sometimes it is compound plus compound or even element plus compound. That's less common, that's a little more rare, but the key piece and what makes this a synthesis reaction is that the second thing that we say here, and that is that the product is always a single compound. And so in a synthesis reaction, we always have a single compound as our product. There aren't two things, there aren't three things, there's only one product, and that's a compound. And so this is our synthesis reaction. Taking a look at our example here, we have Al plus N2, aluminum plus nitrogen. This would be element plus element, and so that says right there, oh, this is going to be a synthesis reaction. In synthesis reaction, they will combine to form, as we said, a single compound. And so that means we're going to make one single compound out of our aluminum and our nitrogen. And so if we do that, they're just going to combine. We get out our periodic table. You look at that. You see aluminum has a valence of +3. Nitrogen would be then the anion, and when nitrogen is an anion, remember it has a valence of -3, and so +3 and -3 balance. So we have Al and we have nitrogen, and so right now just Aln, that's all we have. That balances out here. Now, of course, we do then want to go ahead and balance that equation once we're done with it, because we have one aluminum on the left, one on the right. That's good. But two nitrogens that are on the left, and so we need two on the right. We can't change the subscripts. We just have to put a number out front. So we have 2 Aln on the right. That then changes you to have two aluminums on the right, so we have two on the left. And so our final equation here is 2Al plus N2 yields 2Aln, 2 aluminum nitride. And so this right here would be an example of a fully written out synthesis reaction. On to our next type. The next type of reaction is called a decomposition reaction. If a synthesis reaction is whenever you take two things, two elements or two compounds, and combine them into one, the decomposition is the synthesis reaction in reverse. It's when you start off with a single compound and that compound splits up. And so in a decomposition reaction, the reactant is always a single compound. Now the products, though, define what the products are. That is going to depend on whether the reactant is binary, that is, has two elements in it, or whether it's ternary, that is, it has more than two elements in that reactant. And so if you look at your predicting reaction products colored sheet, this is sort of on the bottom half of the first page. So we see we break this down into binary decomposition reactions and ternary decomposition reactions. Binary reactions are the simple ones, because if we have, say, AlF3, aluminum fluoride, and so if this is a binary decomposition, it's going to break up into its two individual atoms. So for binary decomposition, the products are always individual elements. And so for here, AlF3, when these break up, they're going to break up into their individual elements, which is aluminum plus the other one that's back by itself, which is fluorine. Now, if you remember, we said that there are a class of sort of exceptions for elements that whenever they're by themselves, they are diatomic. And remember we said those are the elements that end in INE and GEN. Aluminum does not end in INE or GEN. Fluorine does end in INE, and so it's going to be F2 when we write that out. And then so this would be a binary decomposition reaction. AlF3 goes or yields Al plus F2. It's not balanced currently. The aluminums are balanced, but the fluorines, we have 3 on the left and 2 on the right. Least common multiple between 3 and 2 is 6. So we put a 2 out front here, and we have to have a 3 out front of this one. That gives us now, though, 2 aluminums on the left, so we have to put a 2 on the right. And so for our binary decomposition reaction, we have 2AlF3 yields 2Al plus 3F2. And so that would be a binary decomposition. What you look for is the reactant just 2 elements? Al and F. It's 2 elements. It's just one thing that's a reactant, though. It's only a single compound. This is going to be a decomposition, and it's going to be a binary decomposition. Now, the ternary decompositions, though, are where things get a little more complex. If you have a ternary decomposition, that means that the compound you start with, that is, that your reactant, has, we said, more than 2 elements. So the 2 examples we have here, H2SO4, 3 elements. AlOH3, 3 elements. It can have 3, it could have more than that. This would be a ternary decomposition. Now, for a ternary decomposition, the fact that you start with one reactant tells you it's a decomposition. The fact it has more than 2 elements tells you it's ternary decomposition. Now you have to look at what type of compound the reactant is. And so on your predicting reaction product sheet, you'll see there's a list of 4 different possibilities that your reactant could be an acid, a hydroxide, a carbonate, or a chlorate. And so for this class, these are the 4 types we're going to use. Obviously, it's possible to have other compounds that decompose that are ternary compositions, other ternary compounds other than these 4, but for this class, we're only going to stick with these 4. It's either going to be a binary decomposition or it's going to be an acid, a hydroxide, a carbonate, or a chlorate. And so each one of those 4 possibilities for ternary decompositions acts differently. And on your colored sheet, you can sort of see it tells you what they're going to make, and we're going to go over that here. So let's suppose that we start off with a case where it's the first one, that the reactant is an acid, H2SO4. We look at this, we say H2SO4, we say first thing, we have 1 reactant, therefore it's decomposition. We say second thing, it has 3 elements, that makes it ternary. Then we look at which of the 4 types of ternary it is. This one starts with H, so this would be an acid here. It doesn't have a hydroxide, no OH in it. It doesn't have a carbonate, no CO3 in it. And it doesn't have a chlorate, no ClO3 in it. So this has to be an acid for H2SO4. And sure enough, it's sulfuric acid. So whenever you have a reactant that's an acid, the products are always water, and it's going to be a nonmetal oxide. And we say nonmetal oxide, there should be a nonmetal that's in here other than the oxygen and other than the hydrogen. And so in this case, the nonmetal is sulfur that sits right here. And so this guy right here, whenever it combines, H2SO4 is going to decompose into water, H2O, plus the nonmetal oxide. And so the nonmetal is sulfur, and then oxide would be oxygen. We do have to balance the valences here. And so we look at our periodic table, and we see that sulfur could be +4 or +6. Now, here's where things start getting a little interesting. We don't know which sulfur this is. And there are 2 ways to go about it. One is to pick one and try to balance it. If the equation doesn't balance, you know you picked the wrong one. If you pick the right one, then it will balance automatically. That's sort of the check and guess method. That's not as good as what we like, but it can work if you actually have to. The better way of doing it is figure out what valence it has in the original compound. And so to do that, what we're going to look at is we say hydrogen is the cation, and so there are 2 of them, so it has a valence of +2. Oxygen is one part of the anion. It's be -2 for 1 oxygen, but there are 4 of them for a total of -8. And so the question is, what does sulfur have to be to get these to balance? Well, -8 plus 2 gives us -6, and so that means the sulfur has to be sulfur -6. And if you take a look at your periodic table, you see that is a possibility for sulfur. I'm sorry, it doesn't -6, it has to be +6. You look at sulfur +6, says +2 plus 6 minus 8 gives you 0. My bad. If you look at sulfur on the periodic table, you'll see that +6 is a possibility for sulfur. So we know that this is sulfur 6, and since this is sulfur 6, that we know we have +6 up here, and we have -2 for oxygen. So how many sulfurs and how many oxygens do we need? We need 3 oxygens, so it's going to be SO3 like this. And so that's how you figure out what the nonmetal oxide is. Now, once you've got that done, you want to balance. And so we have 2 hydrogens on the left, 2 hydrogens on the right. We have 1 sulfur on the left, 1 sulfur on the right. We have 4 oxygens on the left, and now 1 plus 3 is 4 oxygens on the right. We don't have to do anything to balance it. H2SO4 yields H2O plus SO3. And so that's how you'd work out an acid decomposition problem. The next possibility for a ternary decomposition is that you have a hydroxide. So AlOH3, you look at it, you say it is one compound, so we know it's going to be for the reactant, therefore it's a decomposition. It has 3 elements in it, so it's going to be ternary. Is it an acid? Doesn't start with hydrogen, so not an acid. Does it have OH in it? Yes, it does, so it's going to be hydroxide. Hydroxides, if they're reactants, the products are always water and a metal oxide. So very similar to the previous one, only we have a metal oxide instead of a non-metal oxide. So we know we're going to start off with H2O, and then the next part's going to be the metal oxide. The metal here would be, in this case, taking a look at it, is going to be aluminum. And so it's going to be aluminum oxide will be our next piece. And so we're going to add up plus aluminum oxide. We still have to balance these. Aluminum, taking a look at your periodic table, just has a valence of plus 3. Oxygen is negative 2, and so these will balance out nicely. Al2O3. And so that's what we have for that one. Now, to go about this, next thing is to balance the whole thing. We have 1 aluminum that's on the left, 2 on the right, so that means we have to put a 2 out front. Now, doing that, that gives the total of, we have in the hydroxide, there's 1 oxygen, but there are 3 hydroxide, give you a total of 3 oxygens, but there are 2 OH3s, so that gives a total of 6 oxygens. So there's 6 oxygens on the left. On the right now, there are a total of 4, but to get to 6, it's sort of difficult to see exactly how we're going to do that. So let's hold off on the oxygens for right now. Let's go on to the hydrogens. Hydrogen only shows up in one of the 2 products, and so it's going to be easier to balance. And so for the hydrogen, we have a total of 6 hydrogens. That means we have to have a 3 out here. And now if you look at oxygens, over on the right side, we have 3 plus 3 gives us 6, and we have 6 on the left. And so this would be our final balance right here. So 2AlOH3 yields 3H2O plus Al2O3. And so that's how you would do a hydroxide ternary decomposition. So continuing, our next type is going to be a carbonate. And so whenever you have a carbonate that's a decomposition reaction, the products are always carbon dioxide and a metal oxide. And so for this one here, MgCO3, once again, your first step is you're going to notice that this reaction has 1 reactant, which means it's decomposition. MgC and O makes 3 elements in the reactant, so this is going to be a ternary decomposition. Since it's ternary decomposition, we look at the different types of ternary decomposition on your colored sheet. Is it an acid? No, it doesn't start with hydrogen. Is it a hydroxide? No, it doesn't have OH in it. Is it a carbonate? Yes, it has CO3 in it, so this will be a carbonate. The products then, we said, are going to be carbon dioxide, so CO2 plus, our next bit here is a metal oxide. So the question is, what is the metal here? Well, the metal here is going to be magnesium. And so it's going to be magnesium oxide. Now we have to balance the valences on that. Magnesium, if you look on your periodic table, has a valence of plus 2. Oxygen has a valence of negative 2, so those are already balanced. So now we want to balance the whole equation here. We have 1 magnesium on the left, 1 magnesium on the right. So that's good. 1 carbon on the left, 1 carbon on the right. Those balance. 3 oxygens on the left, and 2 plus 1 gives us 3 on the right, so this is already balanced. So MgCO3 yields CO2 plus MgO. That would be the decomposition reaction for a carbonate. Our last different type of ternary decomposition reaction is a chlorate. For chlorates, the way it basically works is the products you get are a metal chloride and oxygen gas. So chlorate decompositions always produce oxygen gas, and then the metal chloride's the second part. So AlCO3, and so for this one, once again, the first thing you should notice is that this has just 1 reactant, and so it's decomposition. It has 3 elements in it, so it's going to be ternary decomposition. You then look at your 4 different types. Is it an acid? No, it doesn't start with hydrogen. Is it a hydroxide? No, it doesn't have OH. Is it a carbonate? Doesn't have CO3, has ClO3. But a chlorate, that'll be the next one, does have ClO3, and so this is going to be a chlorate. It's going to decompose into the metal chloride and oxygen gas. Now the metal chloride, you have to look to find the metal here. The metal here is aluminum, and so it'll be aluminum chloride is what we'll have. So AlCl. Now we have to balance the valences on that. Aluminum is +3, chlorine is -1. So that means to balance them, we have to have AlCl3 plus oxygen gas. But remember that oxygen ends in GEN, oxygen. So when it's by itself, it's going to be O2. And so you always have to be careful to make sure you remember that. Once you've got that, now it's time to balance this guy. We have 1 aluminum over on the left. We have 1 aluminum on the right. That's good. We have 3 chlorines on the left and 3 chlorines on the right. We have 9 oxygens on the left, but only 2 on the right. And so 9 and 2, the least common multiple there, is going to be 18. And so I have to put a 9 in front of this one and a 2 in front of this one. And so in doing so, that's going to give me 2 aluminums. And so I have to put a 2 right there. It's going to give me a total of 6 chlorines, and sure enough, I have 6 chlorines over on the right side. And so that's how you'd basically work out your various types of decomposition problems. Decomposition reactions are probably the most difficult of the ones we have here, simply because you have to go through a lot of steps to do them. But if you follow your colored sheet here, if you say, first figure, is it binary, is it ternary? And if it's ternary, then you say, is it an acid? Is the reactant an acid, a hydroxide, a carbonate, or a chlorate? And then you follow the instructions that are there. It's always going to lead you through. And so let's take a look at our next type of reaction. And so that next type of reaction right here, if I didn't just move the screen on us, put that back, is basically going to be this, a single displacement reaction. And so in a single displacement reaction, what we have is that the reactants are an element in a compound. And for those of you sort of following on your colored sheet, this is the first one on the back. So you have an element plus a compound, or a compound plus an element. Those are your reactants. The products of a single displacement reaction are an element and a compound. Basically what happens in a single displacement reaction is you have a compound, and an element comes along, and an element bumps out one of the 2 elements that's in the compound and joins with the other one. That leaves the bumped out element all alone, and so that's that element that's created afterwards. Typically, in order for this to happen, the element that comes in has to be more what's called active, more reactive, to be able to steal the element that's currently in the compound away. And so in some cases, in reality, these reactions won't actually work. All the ones I'm going to give you for right now, unless I tell you otherwise, are going to be reactions that will occur. And so that's basically what happens in a single displacement reaction. And so in the example we have here, we have Li plus AlF3. We have 2 compounds we're combining here, but since it's element plus compound, that tells you right off the bat that this is going to end up being a single displacement reaction. And so Li plus AlF3. And so for this guy right here, basically what we have happening here is that the lithium is going to come in, and it's going to want to react with either the aluminum or the fluorine. To figure out which one it wants to go with, you have to basically look at the valences. Lithium has a valence of +1. So it's going to want to go with the anion that's on this one here. So lithium's going to want to go with fluorine. In general, the rule is that if the element that comes in by itself is a metal, it's going to want to pair with the anion. If the element that comes in by itself is a non-metal, it's going to want to pair with a cation. And so you just have to look at the valence and see how they balance. So we know we're going to have lithium and fluorine here. Now, to get these to balance, we look at lithium. We said it was +1. Fluorine is -1, and so those already balance. So we got LiF, works just fine, plus the element that got kicked out, the one that's all alone now. That's going to be aluminum. Now, since it's all alone, we do have to ask if it's diatomic or not, and this is aluminum, no GEN, no INE, so it's just Al for what we have here. And so this is how we'd start off with our single displacement reaction. We do still have to balance things. We have 1 lithium on the left, 1 lithium on the right. That's good. 1 aluminum on the left, 1 aluminum on the right. That's good. 3 fluorines on the left, but only 1 on the right. So we're going to have to put a 3 out front to get these to balance. That also gives us 3 lithiums right here. And so now we have 3 lithiums on the left, 3 on the right. 1 aluminum on the left, 1 on the right, and 3 fluorines on the left and 3 fluorines on the right. And so that balances out there. So that's a single displacement reaction. The next type we have is a double displacement reaction. In a double displacement reaction, both reactants are compounds, and both products are compounds. In a double displacement reaction, basically what happens is that we have 2 compounds that combine with each other, and the cations and anions switch positions. And so it's sort of like, 2 couples come to a dance, and then they, at some point during, decide that both couples decide that each person would rather be with the people in the other couple, and so they sort of switch around here. And so what's going to happen is, if we look at the example we have here, we have CO2 plus AlF3, and so carbon dioxide plus aluminum fluoride, and so we say this is compound plus compound. Generally, that's going to give us a double displacement reaction, that the cation in the first one, which is carbon, is going to want to go with the anion in the second one, which is fluorine. And then similarly is that the cation in the second one, aluminum, is going to want to go with the anion in the first one, which is oxygen. And so to work this out, we'd say carbon and fluorine are together. And so we have carbon and fluorine. We've got to balance these two out. Carbon has a valence of +2 or +4 when it's a cation. But we look at what it has over here, and since oxygen is -2, but there are two of them, makes -4. It means carbon has to be +4. So this has to be CF4 because fluorine is -1. And then our other one that's left over here is going to be aluminum and oxygen. And so with aluminum and oxygen, aluminum has a valence of +3, oxygen has a valence of -2. And so to balance those out, we have Al2O3. Now, for our double displacement reaction, we have to balance the whole kit and caboodle. And so to do that, basically what we're going to look at here is that we're going to say, just a second here, I'm going to get that erased. Wasn't quite one to go on me there. We have one carbon on the left and one carbon on the right, so that's good to go. We have 2 oxygens on the left, but 3 on the right. That means we have to find the least common multiple, which is 6. So I'm going to put a 3 out here and going to put a 2 right out there. That should be that's a 2 out front. That's a coefficient. That's a 2. Looking at our next one, we have aluminum. We have 1 aluminum on the left. We have 4 aluminums that are on the right now because we have a 2 down here, and then the 2 we put as a coefficient out here. Makes a total of 4. So we're going to put a 4 out in front of this guy. And if we have a 4 right there, then that's going to give us a total of 12 fluorines over here, because 4 times 3 gives us 12. So I have to have a 3 out in front of the carbon. But that gives me 3 carbons on the right, and then if I look on the left, I also have 3 carbons. And so this is the one that's to balance. This is how this balances out. In general, is the double displacement are one of the 2 most difficult ones to balance after you've written out the equation. And but it still works the same way as we just saw right here. Just take the cations and anions and have them switch positions, and then balance them with respect to their valences once you've figured out the products. Now, probably the most difficult one to balance in general, not always, but in general, is going to be our next type of reaction, which is our combustion or oxidation reaction. As we said, both names are acceptable for this reaction for this class. Usually combustion is what happens if the reaction is a little faster, like say if we're setting something like a piece of paper on fire. That's a very quick reaction. It is an oxidation reaction, but it's a quick one, so we call it combustion. The paper's combusting. On the other hand, when iron rusts, iron rusting is also an oxidation reaction, but you wouldn't call that generally a combustion reaction because rusting is a very slow process. It is oxidation but not combustion in a technical sense. For the purposes of what we're going to do here, though, we will accept either name. So, in an oxidation reaction or combustion reaction, the reactants are oxygen gas and some other element or some other compound. So we basically take oxygen plus something else, and that's going to give us our oxidation reaction. The products are going to be 2 different compounds. So we have some element or some compound plus oxygen yields a compound and another compound. Okay? And so most cases when we run across oxidation or combustion reactions, the element that's coming in or the compound that we're combining with oxygen gas is a hydrocarbon. And when we say hydrocarbon, basically what we mean is it's composed of no elements other than hydrogen, carbon, and oxygen, and it has to have carbon. And so typically is that hydrocarbon would be something like CH4 would be a hydrocarbon, something like H12O would be a hydrocarbon. Those would be examples of hydrocarbons. Basically, they just have carbon, hydrogen, oxygen. They don't necessarily have to have oxygen, but they do have to have carbon, and they pretty much almost always have hydrogen in them too. Well, they have to have hydrogen in them too. So if the non-oxygen reactant is a hydrocarbon, in that case, special case, this makes it easy for you. The products are carbon dioxide and water. Period. That's it. No balancing of the individual ones. You have to balance the whole equation, but no balancing the individual ones you have to do. So taking a look what we have here, C5H12 plus O2 is that what should tip you off here, it's compound plus element, but the element is oxygen, it is O2, and so because the fact that element is oxygen down there, that basically you're going to say, this is an oxidation reaction. Now, the one that we're pulling in, C5H12, that's carbon and hydrogen. That means this is a hydrocarbon. Whenever we have this hydrocarbon plus oxygen, it's simply going to give us products, carbon dioxide and water. And so to write this out, we say CO2 plus H2O, just like that. Now we simply just have to balance it. On your right side, or your left side, you have 5 carbons. On your left side, you have 5 carbons. On your right, you have 1. So we put a 5 out front here. We have 12 hydrogens that are on your left side, only 2 on your right, so we put a 6 out over there. In doing so, we end up with, we have 2 oxygens on the left. We have 5 times 2 gives us 10 over here, plus 6 right here. 6 times 1 is 6. That gives a total of 16 oxygens. And so I put an 8 out here to get this to balance. And so this would be the proper balancing of this particular oxidation or combustion reaction. C5H12 plus 8O2 yields 5CO2 plus 6H2O. These usually are the hardest ones to balance, in my personal opinion. Oftentimes you're going to have to sort of go around in a little bit of a loop, is that you'll balance it out and then you'll change one thing which will change everything else. That does happen sometimes. If you go through that loop more than twice, then you probably made a mistake in something else that you did. And that's true for any balancing of equations. But overall, these are your 5 types of reactions. Let's do a little practice to get used to identifying which ones are which and solving them out. So our first one here, C3H6 plus O2. So in this case, we have a compound plus an element, but the key part here is what is the element? The element is oxygen. So since the element is oxygen here, oxygen plus a compound is going to be an oxidation reaction. C3H6 is a hydrocarbon, and so that makes this one easy. We know that this is oxidation and hydrocarbon, so it's going to be just CO2 plus H2O is what we get for our products. Now we have to balance it. We have 3 carbons on the left and 1 on the right, so we put a 3 up here. We have 6 hydrogens on the left and 2 on the right. We put a 3 right there. And doing this, oxygens, we have 2 on the left. On the right, we have 6 that's right here, and then 3 that's right here gives us 9. But 9 and 2 don't work. We're going to have to go up a step. We're going to have to double what we've got here. And so we're looking for the least common multiple between 9 and 2, and that's 18. So we're going to have to put a 9 out here to make this 18. And in doing that, we have to double everything else that we had before. And so that means we're going to have to erase some stuff in here. I think we can do it without messing up everything else. We have 18, which means that we're going to have, instead of having 3 carbons out here, we're going to have 6 to start with right here. And instead of having 3 out there, we're going to have 6 right here. And so if we do this, then now, make sure that I'm working this out right, we have 9 times 2 gives us 18 over here. We have a total of 6 times 2, which gives us 12 carbons on this side. 6 times 1, I'm sorry, 6 times 1 gives us 6 on this side. 12 plus 6 gives us 18, and then 9 times 2 gives us 18, and so that works out. Now, we do now have to change our carbons. We have on the right side 6 carbons now. We have on the left side just 3, so we put a 2 out front. Now, that gives us 2 times 6, 12 hydrogens on the left, and we have 6 times 2, 12 hydrogens on the right. And so this balances out. And so as you can see, these oxidation or combustion reactions can get complex pretty quickly. And so that's basically how you work that one out, and that's what we'd get for that particular combustion reaction. Let's take a look at the next one. Na plus N2. Element plus element. Whenever you see element plus element, you think synthesis. And so with a synthesis reaction, we're simply combining these two. And so we have Na and N that are going together. Na, sodium, has a valence of +1. Nitrogen here is an anion, and when it's an anion, it has a valence of -3. And so this has to be Na3N to work this out. Now, if we take a look at to balance the whole equation, is we have 1 sodium on the left and 3 on the right, so we put a 3 out front. We have 2 nitrogens on the left and only 1 on the right, so we have to put a 2 out front of that. But that then changes the number of sodium. Now we have 6 sodiums on the right, and so we are going to change our front. Oh, I don't know what I just did there. Should be 6 on the right over there, but give me just a second while I see if I can modify what I just undo what I did here. Boop, boop, boop. I went to the wrong one entirely. I don't know how I did that. Give me just a second as I pause this, and I'll be back in just a second. So continuing there, we have, to get this to work, we said that we've got 2 Na3N. We have 2 N's on the left and 2 N's on the right. For NAs, we have 1 Na on the left and now 6 on the right. So we have to put a 6 right here, and that balances that guy out. On our next one, we have SnOH4. And so we notice we just have 1 reactant. That tells us it's going to be a decomposition reaction. We say how many elements it have. It has tin and oxygen and hydrogen. That's 3, so it's a ternary decomposition. If it's ternary, we're going to make sure we see which one is it. Is it acid, hydroxide, carbonate, or chlorate? And so is it an acid? Nope, doesn't start with hydrogen. Is it a hydroxide? Yes, it has an OH sitting right down in there. And so that's going to tell us it's hydroxide. And if you look at your color sheet, your predicting reaction product sheet, you see hydroxides are going to they decompose to form water and the metal oxide. And so the first piece that's right here is going to be water. And so we have H2O plus, it says next it's going to form, we said, the metal oxide. The metal here is going to be tin, Sn. So we have Sn and O. Now, what valence does it have? We look at tin on there, and tin is either +2 or +4. So we have to figure out which one it is. And we know hydroxide is -1. And so since we have 4 hydroxides, that means the total valence is -4, which means the tin has to be +4. So this is tin 4 oxide over here on the right. Since oxygen is -2, to balance out the 4, it has to be SnO2. And so these would be the products, water and tin 4 oxide. And now to balance the rest of it, we're going to make sure we look and we have 1 tin on the left and 1 tin on the right. We have 4 oxygens on the left, and right now we only have 3 on the right. That one's a little bit difficult to balance though because we have oxygens 2 different places. So let's look at the hydrogen first. We have on the left 4 hydrogens, and we have 2 on the right. So we can put a 2 right here. That gives us 4 hydrogens. That, notice, also changes our number of oxygens. Now on the right we have 2 times 1 is 2 plus 2 that's over there, and so it gives a total of 4. And sure enough, we have 4 on the left, and so this balances out. And so that would be that decomposition problem. Our next one, H2SO4 plus MgClO in parentheses 2. Sulfuric acid plus magnesium hypochlorite. And so in this case, it's compound plus compound. This is going to be a double displacement reaction. They're just going to switch spots on us. And so that means that the cation on the first one wants to go with the anion on the second one, and the cation on the second one wants to go with the anion on the first one. And so to do this, we're going to end up having hydrogen and the hypochlorite, ClO. Now, hydrogen has a valence of +1. Hypochlorite has a valence of -1, so that just balances out nicely. Don't have to do anything to it. Our next one is going to be, our cation is magnesium. Our anion is sulfate, SO4. Magnesium has a valence of +2. Sulfate has a valence of -2. So that one balances without any trouble there. Now we have to balance the whole equation. We have 2 hydrogens on the left and 1 on the right, so we put a 2 out front. We have 1, so in this case the sulfate, the polyatomic ion right here, stays in one place. So we can just treat this like one whole piece. And so we have 1 sulfate that's over on the left, and we have 1 sulfate on the right, so that works. Magnesium, we have 1 on the left and 1 on the right. Hypochlorite, once again, it stays as a whole piece here. And so there are 2 on the left and, sure enough, 2 on the right. And so this would be our final balancing here. H2SO4 plus MgClO2 yields 2HClO plus MgSO4. And so that being said, that should go ahead and finish things up for this. And so that will end this lesson.